Fertilization can increase overall Christmas tree productivity. Hello, I'm Russ Briggs, Professor of Forest Soils at the SUNY College of Environmental Science and Forestry. I'm here at Heiberg Memorial Forest, one of our research campuses. It can take as long as 10 to 15 years for this seedling to grow to a saleable Christmas tree. That period of time is referred to as the rotation age. One way to reduce the rotation age is to increase the growth rate. Fertilization is one of the tools that can be used to increase that growth rate and reduce the rotation age. Reducing the rotation age has a significant impact on costs. Fertilization is an important tool that can be used to enhance Christmas tree production, increasing tree quality and decreasing the rotation age. Shaving 2 to 5 years in the rotation can significantly reduce production and carrying costs. Consequently, it is important to put it in proper perspective with an overview of Christmas tree production. The whole process begins with site selection and the decision of which tree species to plant. Next, tree spacing is decided upon and flags are placed where the trees are to be planted. The vegetation, the weeds, and the trees are planted. As the trees grow, weeds must be periodically controlled, a process referred to as vegetation management. As the trees get older, they are sheared each year to enhance their shape and appearance. Finally, we get to the topic of fertilization. Fertilizer can be applied to increase tree growth. The decision of if and when to fertilize requires some additional information, which actually brings us back to the concept of site. The term site refers to the physical environment that the tree is placed. When you think about the factors that constrain tree growth, the practical importance of identifying site quality become obvious. Carbon dioxide, temperature, light, competition, quality and quantity of the root exploitable soil volume. These are the constraints that can be managed: light, competition, quality and quantity of the root exploitable soil volume. Light is managed during plantation layout by controlling spacing, and it's also partially managed in the early years by controlling competition. The quantity and quality of soil volume is dictated partially at the beginning of the process when you select the site. Here's where fertilization fits in. That brings us to the concept of site quality. You can really think about site quality as a relative measure of the vegetative production capacity of a site for a given purpose. It consists of 3 components: product amount, time period, and unit area. For instance, the average diameter growth per a given tree over a field or an acre, or pounds of foliage in an acre in a year. Site quality is determined by the effective nutrient supply and effective water supply, schematically represented here in this graph by Dr. Earl Stone. High-quality sites, which produce good tree growth every year, have an adequate supply of nutrients as well as an adequate supply of moisture. If you reduce effective moisture, production or site quality will decrease, even if there are plenty of available nutrients. Reversing the situation and reducing nutrient supply while having adequate moisture will also reduce site quality. Quality and quantity of the root exploitable soil volume is controlled by soil depth, which can be limited by impermeable surfaces such as bedrock or hardpan, or even a seasonally high water table. Soil volume can also be reduced by coarse fragments or rocks. Soil texture influences water holding capacity and fertility. Sandy soils have low water holding capacity and low organic matter. They tend to be low in available plant nutrients. Clay soils, on the other hand, tend to be poorly aerated, but are often high in nutrient supplying power. Loams are the best of all worlds, with good aeration, water holding capacity, and fertility. Seasonally high water tables during the growing season result in poor aeration, leading to gray color produced when iron is reduced. When the water table drops later in the growing season, iron is oxidized and appears orange and red. The alternating raising and lowering of the water table during the growing season results in a combination of gray and orange referred to as mottling. This is the morphological footprint of the fluctuating water table. Soil drainage classes ranging from excessively well-drained to very poorly drained are defined on the basis of depth to seasonally high water table. It should be apparent that Christmas tree production will be most favorable on the better drained sites. Let's examine several profiles and identify the constraints of tree growth. The soil profile is limited by soil depth. Both nutrients and water together will limit tree growth. The little bit of soil is filled with rock fragments, reducing soil volume. This sandy soil is mottled in the upper 5 inches and has a dull gray color below, indicating poor drainage. The constraint here is excess moisture. This deep sandy soil is limited by lack of water. In summary, site quality can be constrained by water, too much as well as too little, limited nutrient availability, alone or in combination with water. Root exploitable soil volume can be reduced by shallow depth to root restricting layer, a perched water table, or excess coarse fragments. Tree species vary in their capacity to tolerate too little or too much moisture. The spruces generally tolerate excess moisture, while Fraser fir is very sensitive to moisture and will do poorly on wet sites. When nutrition is the limiting factor, fertilization will increase tree growth. The barrel analogy illustrates the concept. Growth rate is represented by the height of the water in the bucket. If nitrogen is limiting, the addition of N eliminates the constraint, effectively plugging that hole, and the level of water in the bucket rises until the next limitation is encountered. In this case, it would be soil conditions. If, on the other hand, excess water constrained growth in this site, the addition of N fertilizer would not affect growth, as shown here. From a practical point of view, it follows that fertilizing Fraser fir exhibiting poor growth and yellow needles on a wet site will not solve the problem. The constraint could be corrected with some cost by tile drainage, but not by addition of fertilizer. In order to have an effective nutrient management program, identifying nutrient deficiencies is needed. Visual symptoms are not very reliable for detecting which nutrient is limiting growth. Many nutrient deficiencies exhibit similar results. This relationship between growth response and foliar nutrients varies by species and nutrient. Using a series of fertilizer trials, this relationship is established. Foliar concentrations associated with low levels of growth indicate a deficiency. Nutrient addition beyond that required by plants can eventually cause reduced growth and even toxicity. Carbon, hydrogen, and oxygen, which are obtained from air and water, comprise about 90% of the plant dry weight. Nitrogen is fourth, comprising about 3% of plant tissue dry weight. Generally, nitrogen is the element most likely to limit plant growth. Our experience shows that application of N fertilizer will produce a positive response 50 or 60% of the time. After nitrogen, phosphorus is the next macronutrient likely to limit growth. Concentrations of phosphorus in plant tissue are much smaller than that of N, generally about 10% of N concentrations. The presence of mycorrhizal fungi, which infect tree roots and increase absorption of Phe, is an important factor in phosphorus nutrition. For these reasons, our research has focused on nitrogen. Foliar concentrations change over the growing season, as shown here for red pine. The changes are minimal in the fall after the buds harden off. Foliar samples are usually taken in the fall. Conifers carry multiple age classes of needles. For foliar analysis, we utilize the current year needles. We need about a 10-gram sample of dry weight. Since needles are about 100% moisture, this translates to about 20 grams of fresh weight. Clip the samples for 2 or 3 trees and store them in a paper bag in the refrigerator. Be sure to label the bag with the species and field location. The samples must be kept cool to prevent respiration, which would change the foliage weight and provide an inaccurate nutrient concentration. The cooled samples should be sent to the Forest Soils Lab at ESF. The sample will cost $20 to cover the reagents and the technician time. As soon as the clipped branch samples arrive at ESF, they are placed in a drying oven at 60 degrees centigrade for 24 hours to stop respiration. The samples are removed from the oven and brought into the sample preparation lab. Needles are stripped from twigs in preparation for chemical analysis. The needles are ground in a Wiley mill to pass a 20-mesh sieve and then placed in an amber bottle. The ground material is dried in an oven at 60 degrees centigrade to remove the moisture. Ground material is removed from the oven and cooled in a desiccator so the sample will not absorb moisture from the air during the weighing process. A sample is weighed into filter paper and placed in the digestion flask. We add digestion material, and then concentrated sulfuric acid is added down the side of the flask. Organically bound nitrogen is being converted to ammonium as the flask is heated. The flask is allowed to cool and distilled water is added. Now we're ready for the distillation procedure. Nitrogen, now in the form of ammonium, is distilled as ammonia gas and collected in a flask of boric acid. Pieces of zinc are added to the distillation flask as boiling chips. Concentrated sodium hydroxide is poured down the side of the flask into the bottom without mixing. The flask is connected to the distillation trap and heated until about 150 ml of distillate has been collected. The boric acid turns from blue-purple to blue-green as ammonia is introduced. The ammonium solution is titrated with 10th normal hydrochloric acid until the solution turns from blue-green to pink. Nitrogen concentration of our foliage sample is computed on the basis of the volume of hydrochloric acid added. We have gone through a process that begins with twig collection and transport to the lab, drying, grinding, digestion, distillation, and finally titration. You can see why this procedure is costly. The resulting foliar nitrogen concentrations are compared to the critical values that were developed recently from the fertilization study. This study was supported by New York State Ag and Markets and the Christmas Tree Farmers Association of New York. If the nitrogen concentrations are below these values, the addition of N fertilizer is likely to produce increased growth. Different inorganic fertilizers vary in the proportion of nitrogen that they contain. Among the granular fertilizers, urea, at 46% nitrogen, has the highest proportion of N. Ammonium sulfate also provides sulfur, a macronutrient. The choice of which fertilizer to use depends largely on the logistical concerns, such as availability and price. Fertilizer composition can be tailored to individual growers. The amount of fertilizer to add depends on the formulation. This leads us to the concept of the fertilizer guarantee. All fertilizers are labeled with %N, % phosphate, or P2O5, and % potash, K2O. Based on our discussion about nitrogen fertilizers, what would you call the fertilizer that is labeled 4600? Urea. How much of this urea, this 4600 fertilizer, is needed per tree? Well, 46% of the fertilizer is nitrogen. To convert to a decimal percent, part per 100, we divide by 100. 46% is the same as 0.46. Now for some algebra. 46% of our unknown amount of fertilizer equals 1 ounce. If we let x represent the unknown amount of fertilizer, we can write this statement as 0.46 times x equals 1 ounce. Dividing both sides of the equation by 0.46 gets our unknown on one side of the equation. Now, solving the equation, x is equal to 1 divided by 0.46. My trusty calculator tells me the answer is 2.17, or approximately 2 ounces. So it takes 2 ounces of urea fertilizer to deliver 1 ounce of nitrogen to an individual tree. Suppose we use a different fertilizer, say 10-10-10, which is commonly available. How much 10-10-10 fertilizer is needed per tree to provide that 1 ounce of nitrogen? Remember that 10% is equal to 10 over 100, or you can write that as 0.10. So 10% of X fertilizer equals 1 ounce. 0.01 times X equals 1 ounce. X, the amount of fertilizer needed, is equal to 1 ounce divided by 0.10, or 10 ounces. Essentially, 10 ounces of 10-0-0 provides 1 ounce of nitrogen. That is considerably more fertilizer per tree than urea, which is 46% nitrogen. If you use 10-10-10, you also applied some phosphorus and potassium. How much? Unlike nitrogen, number includes some oxygen because it represents the proportion of P2O5, phosphate. The question really becomes how much P is in P2O5 on a weight basis. That's easily solved by knowing the molecular weights. The molecular weight for phosphorus is 31, for oxygen is 16. These data you can get from a periodic table. For phosphorus, there are two of them, so 2 times 31, 62 grams. For oxygen, there are 5 of them in that compound, and 5 times 16 equal to 80 grams. So the total molecular weight for P2O5 is 142 grams. Now the proportion of P in P2O5 is equal to 62 over 142, or 0.437. The fertilizer is 10% P2O5, so 0.437 times 10%, 0.10, is equal to 0.0437, or 4.347% of that fertilizer is P. 0.0437 times 1 ounce is equal to 0.0437 ounces of P. So with that 1 ounce of 10-10-10, you also applied 0.04 ounces of P, considerably smaller quantity compared to nitrogen. Finally, we can go through the same exercise for potassium, K. This fertilizer has 10% K2O. The molecular weight of potassium is 39. The molecular weight of oxygen is 16. For potassium, there are 2 of them, so 2 times 39 is equal to 78 grams. For oxygen, there's 1 of them, and 1 times 16 is equal to 16 grams. The total weight for the compound K2O is the sum, 94 grams. Now the proportion of K and K2O is 78 over 94, or 0.830. 0.830 times that 10%, 0.10, is equal to 0.083. Essentially, 8.3% of the fertilizer is potassium. 0.830 times 1 ounce is equal to 0.83 ounces of potassium. So that 1 ounce of fertilizer has provided 0.8 of an ounce of potassium. Well, I'm back at Heiberg Forest to demonstrate individual tree fertilization. These balsam fir had foliar concentrations of nitrogen of 1.4%. That's a bit lower than the critical value. That suggests that these are going to respond positively to fertilization. Now I've got a couple of ways to deliver that nitrogen. We usually deliver 1 ounce. Here we have 10-10-10. 10% nitrogen, 10% phosphate, and 10% potash. On the other hand, we have urea. Urea is 46% N. No phosphate, no potash. We're going to put this just around the drip line, this NPK. Now this is nitrogen, phosphorus, and potassium. It's going to do a lot for the tree. Nitrogen is one of the critical elements. They build up the nutrition and also good for photosynthesis and protein. So we'll just broadcast that, and that's all there is to it. Then we'll move to the next tree. We'll just use the urea. Urea, this 1 ounce of nitrogen fertilizer only weighs 2.2 ounces of fertilizer. And we'll do the same thing. We'll distribute that around the drip line. And the same nitrogen, no phosphate, no potash. And that's pretty much all there is to it. Next, we'll demonstrate how to fertilize on a large area basis. Some operations are too large to handle fertilizing on an individual tree basis. In that case, we'll go and fertilize on an area basis. The recommended rate for nitrogen is about 110 pounds per acre. On a square foot basis, that translates to about a pound of nitrogen in 400 square feet. Now I'm using 10-10-10, we've seen that before. This is 10% nitrogen. So I need 10 pounds to deliver that 1 pound of nitrogen. Now I've measured this out. This is 50 foot long by 8 foot wide. And now we'll finish up. Let's go with it. As you can see, it took a tremendous amount of planning and maintenance to bring the trees to this point. These trees are healthy and full. Fertilization has reduced the rotation age and increased the growth rate. A good fertilizer program can increase the productivity of your Christmas tree plantation. I'm Russ Briggs.